And today we will just go through some important aspect of a vector space, which usually participants find it difficult. And then what is the null space or the dimension of a vector space, and so on. Some important results on vector space we will be revising today in this live session. So first of all, this vector space, so we should not be find it difficult to understand, because this is a special set, nothing else. So vector space, it is a set V which has certain properties. First of all, the elements of this vector space is called vector, or the elements are called vectors. It has nothing to do exactly with the vectors we have studied, which have directions and its absolute value, etc. So here we are talking about, in a more general sense, that the elements of this set are called vectors. So what are the properties of this set? That is this what is stated on this slide here. So first of all, we need to define two binary algebraic operations, which are called vector addition and scalar multiplication. So depending on how we are defining the addition there of the elements of this vector space and what is scalar multiplication, then we will call this vector space, this set, as a vector space. So what are the properties? Some important properties are the closure properties. So we need to define, of course, as I said, these two binary algebraic operations. One is called vector addition, another one is scalar multiplication. So when we add two vectors with respect to, of course, the defined vector addition. So if we add two vectors, the sum of these two vectors must be there in that set itself. That is the first property. And the second property is here, that lambda belongs to this set of real numbers, which is also can be generalized to what we call field, but here I'm just restricting this vector space over this R. So this R is not necessarily, it has to be set of real numbers, but it can be again a more general set which is called field, but I'm not going into those details. So this is a vector space over R. So this R is important. What we are considering here, set of real numbers, and this vector addition, scalar multiplication, and this set R. So these three things we need to define the properties of this special set, which we will be calling as vector space. So the first property we have discussed. The second important property, we have this this lambda, which is called the scalar. So it's a part of this set R. So this lambda times u, that means this is scalar multiplication. We are doing multiplication with this scalar lambda to this u. This should belongs to this special set itself for all values of lambda from this set R, and for all u from V. So this should be also defined, and this product lambda times u should be also there in this special set. So these two properties are very, very important, and there are many more which I will not go through all into the details. You can go through the lectures again. So these are like a commutativity property, which is u plus v is equal to v plus u. So they can commute with each other. There is a associativity property. That means you add u into v plus w, or you first add u and v and then into w. It should be the same. There should be a zero vector in V. The property is that if you add this zero vector with this, of course, defined vector addition to this vector, zero vector, which we are calling, nothing should change to the vector. So this is called zero vector. It should be there with respect to that addition which we have defined. And there are many more properties, but as I said, the closure properties plays very, very important role to define this vector space. The examples, if we talk about the vector space Rn, so this Rn over this special, the another set which I was talking about, which could be generalized to more general set, which is called field. So this vector space Rn over this R is a vector space when we define the vector addition as this very usual way that these component-wise addition will be there of each component here. And this scalar multiplication is defined in this way. So what we are considering here, we are considering this over this R, and this is the vector addition, and this is the scalar multiplication. In that case, this set Rn, which is the set of all ordered n tuples, is a vector space. One can check all the properties which we have stated on the previous slide, that they are satisfied in this particular case. Another example, which is a very practical one, that the solution of the system of homogeneous equation, that is Ax is equal to 0, this forms a vector space, the solution set. So all the solutions of Ax is equal to 0, they form a vector space, or the set of solutions of Ax is equal to 0, they form a vector space. That means this V is a set of X belongs to Rn, and how we are choosing these X, or rather the notation says here Xn, we can put it that Axn is 0. That means this Xn is the solution of the equation Ax is equal to 0. So all possible solutions, if we collect, this is a vector space, and there is a special name for this vector space also. This is called null space of A, null space of this matrix A. So not that this V, and which is a subset of Rn. This is a subset of Rn. Rn is also a vector space, and this is a subset which is also a vector space, and therefore in this setting we call that this is a vector subspace. Yeah, we call this V as vector subspace, because this is a vector space and also subset of the vector space. We call it vector subspace. Okay, so the subspace, as mentioned there, this is a vector space, of course. So V is a vector space, and W be a subset of the vector space V. Then W is a subspace of V if W itself is a vector space over the same field R with respect to the same operation as in V. Then we call it as vector subspace of V. The criteria, because we have the same operation, and this is a part of the vector space only, subset of a vector space, we do not need to check all the properties which we have mentioned there. They will be automatically satisfied. What we need to check only these two properties, that the sum of the two elements belongs to this subset, and also this scalar multiplication lambda u must belongs to W again. So these two properties we need to check, and if these two properties are satisfied, then this will form a vector space, which is a vector subspace, rather to say, of V. Well, before we proceed for more interesting stuff, we need to make it clear that what is a linear combination of vectors. So vectors here, we are talking about the elements of our vector space. So an expression of this form lambda 1 v1, lambda 2 v2, lambda n vn, where lambda I is this lambda 1, lambda 2, lambda n, they belong to the set of real numbers. This is called a linear combination of vectors v1, v2, v3, vn. So just a remark that if V belongs to the vector space V over R, it's a linear combination of V1, V2, V3, Vn in R if there exist scalars from this field R such that V can be written as a linear combination of these vectors. So we call that vector V a linear combination of these vectors if there exist scalars lambda i's, so that the linear combination of these vectors gives you V. All right. Linear independence of vectors. So let's say V is a vector space. A finite set of vectors, the finite set of vectors. So by the way, we are considering all these vector space which has dimension finite, which I will be talking about what is the dimension of the vector space. That means we need to wait just for one more slides to be over. So let V be a vector space. A finite set of vector of V is said to be linearly independent if this combination equal to 0, if we set this linear combination equal to 0, that should implies that the only possibility when you can set them to 0, all the lambdas must be 0. This is the meaning of linearly independent set. So just an example that if you want to investigate the linear dependence or independence of these vectors, or we want to show rather that these vectors are linearly independent or not, what we need to show that their linear combination, that means lambda 1 v1, lambda 2 v2, lambda 3 v3, we will set equal to 0 vector. That means because the v1 will come from here, so this is multiplied by lambda 1, this will be multiplied by lambda 2, this will be lambda 3, and when we add with the usual addition of in this R3, this will be like lambda 1 plus 0 lambda 2, then 0 lambda 3, so we'll get lambda 1 only. Similarly, the second component, third component, and this is equal to that 0 vector, which is 0, 0, 0. Once we solve this, it's easy because the lambda 1 has to be 0, what we realized from the first, comparing the first component, and then comparing the second one, if lambda 1 is 0, lambda 2 has to be 0, and if lambda 2 is 0, then lambda 3 has to be 0. So all these are 0, and therefore we can say that this given set of vectors here, or the given vectors, are linearly independent. Okay, so there is another term here which we are going to explain, that the vectors here, they form a spanning set of R3. What do we mean by spanning set of R3? That using these vectors, we can span, or we can construct the whole R3. That, I mean, any element of R3 can be written as linear combination of these 4 vectors. If this is the case, we call it that they form a spanning set. They form a spanning set. Any vector you take from R3, they can be expressed as lambda 1, this v1, lambda 2, v2, lambda 3, v3, and lambda 4, v4, where this is, let's say, v1, this is v2, this is v3, and this is v4. So this is the idea here, and then for any vector v1, v2, v3 from R3, we can write down this is equal to lambda 1, this v1, lambda 2, v3, and so on. And now we, because this is a set of, this is just the system of linear equations, nothing else, where the first equation you can see lambda 1, then we have lambda 2, then we have here lambda 3, and then we have lambda 4, which is equal to v1. Similarly, the second equation and the third equation, and then this is written here in matrix form or augmented matrix form. And then as we know that Gauss elimination can be used here to put into this echelon form, and where we can realize that yes, indeed, we have the solution for this system. We have the solution for this system. Indeed, we have infinitely many solutions, and that's enough to say spanning set. That means any vector we give v1, v2, v3, vn, a general vector we have taken, and we found that we can get the lambdas which here shows that there are infinitely many possibilities of these linear combinations to produce any vector there. But the key point is that we can find any vector in terms of these given vectors as a linear combination. So there is a non-unique representation, that's fine. So because there are infinitely many solutions exist to this system, but yes, we can express any given vector in form of all these vectors. Well, the vectors this do not span R3. Yeah, this is what we will show here, that these vectors, the vectors 1, 2, 3, 1, 3, 4, and 1, 5, 9, they do not span R3. Why they do not span R3? Because for any vector v1, v2, v3 from R3, if we write again, or we try to write that lambda 1, v1, lambda 2, v2, lambda 3, v3, what will happen when you put into the echelon form, we will realize that there is no uh, solution to the system, because you are getting the situation that 0 is equal to something which may not be 0, because we are considering this for any vector, and therefore it doesn't have solution. So it cannot, these three vectors cannot span R3. This is what clear from here. Earlier we had taken 4 vectors and we have realized that they can span whole R3, but these 3 vectors cannot span whole R3. This is the idea of the spanning set here. Now I can come easily to the basis and the dimension of a vector space, which is a very important concept. So basis is the linearly independent set that span a vector space V. So first of all, the basis is a spanning set. That means any vector from the vector space V can be expressed in terms as a linear combination of these given vectors. Then only we can talk about the basis, but there is an additional requirement that they has to be linearly independent. So spanning set is not enough, but the linearly independent spanning set is what give you the basis. And the number of elements in the basis is called the dimension, because what we can also prove this, that the number of elements in any basis, because basis is not unique, you can have several bases, but the number of elements going to be the same, and that is called the dimension of the vector space. So not that every vector space we can be written, and that's a unique way of writing as a linear combination of the basis of vectors. In one of the examples, just 2 slides before, we have seen it was these given vectors were forming a spanning set of a given vector space, but there was a non-unique representation. So those non-unique representation, because of those non-unique representation, we will realize that they cannot form a basis, because once you have the basis, you have the linearly independent vectors in the spanning set, then we have a unique representation of any element in V. So in this case, the example which we have discussed, which was a spanning set, certainly their elements were not linearly independent. The vector space V, this vector space 0 is defined to have dimension 0, because we do not have any linearly independent vectors in this 0 set. Okay, so another important part where this concept of vector space can be discussed in the setting of linear mapping or linear transformation. So let X and Y be any 2 vector spaces. A mapping fx to y is called linear mapping or linear transformation if it satisfies the following 2 conditions. What are those following 2 conditions? That once you apply this linear map to u plus v, you will get fu and plus fv. For any scalar k and vector u, you have fku is equal to k times fu. So these 2 properties need to be satisfied for this mapping here f. And then the 2 conditions above can be combined into one, that f of k1u plus k2v is equal to K1 FU and plus K2 FV, where K1 and K2 are scalars and UV belongs to that vector space V. Again, another important property which can easily be checked, that F0 is 0. That means the 0 elements from this X vector space will be mapped to 0 of the Y vector space. So every linear mapping takes the 0 vector into the 0 vector. Okay, so next we have this example which is given by F, the linear map from R3 to R3 given by this XYZ2, which is mapping to XY0. So we'll check that this is a linear map. So we take any two elements, A, B, C, and A dash, B dash, and C dash. Then if we apply this F on U plus V, we will get F A plus A dash, B plus B dash, C plus C dash, and then applying this transformation, we will get this vector, which can be written again AB0, A dash, B dash 0, and which is nothing but FU and FV. So for any scalar K, you have FKU is equal to F KA, KB, KC, which as per the definition of this transformation, we have KA, KB, comma 0, which can be written as again KAB0, which is nothing but KFU. So F is a linear transformation because these two properties we have checked for this given transformation. So there is a concept of the kernel and image of linear mapping. So let's consider F is a linear map, which is from X to Y, and we call kernel of all those X we have collected from F whose image is 0, that is Fx is 0. 0 element of this Y. So image of F, so all those Y's in Y where there exists a X such that Fx is equal to Y, so simple image. And the example, for example, in this mapping, the image of F will be all these ABC where the C is 0. So this is basically nothing but the XY plane. And the kernel, if we talk that if we set here A and B, we take A, B to 0, automatically it will map to 0. So all those elements we take where the first two are 0 and C can be anything, that will map to 0, 0, 0. So that means this is nothing but the z-axis. So this is the image of F. There is a nice result that if F is a linear map, then the kernel of F and the is a subspace of X, and also image is a subspace of X. That one can easily show, which I'll skip here. And there is another result which again not difficult to prove, and I guess in the lecture we have already gone through it. So the theorem says that suppose this x1, x2, xm, they span the vector space X, and suppose there is a linear map, then this fx1, fx2, fxn, they will span image F. This is a very important result, that we have a spanning set of vector X, and then we have the spanning set of image itself. So we can tell something about the image, we can find out the basis of the image, we can dimension of the image once we have this spanning set of the X. Using this, we have a very important result which is called rank and nullity theorem. So f x to y is a linear map, then the rank of F is defined as the dimension of the image, because the image is a linear, is a vector space, and whose dimension is nothing but the rank of F. The nullity of F is the dimension of the kernel of F. And this theorem now defining this rank and nullity in this way, what we have, that if X is a vector space of finite dimension and let f x to y be a linear map, then what we have, that rank of F plus nullity of F is equal to dimension of X. So rank plus nullity gives you the dimension of X. It has a lot of applications, this theorem, an important result which can tell about the rank once the dimension and the nullity is given, or we can find out the nullity when the dimension and rank is given, and so on. So I will end with this example where we have a mapping R4 to R3. It's a linear map which is defined with this transformation f x y z t is given by this transformation. So this is, as you can see, this is R4. The element of R4 is mapped to element of the element of R4 is mapped to the element of R3. So we have three tuples here. So find a basis and the dimension of the image and the kernel. These two things we have to find, the image f and the kernel of f. So image of f can easily be found because we have the result. We know already from R4 that this E1, E2, E3, and E4, the standard basis. The E1 means 1, 0, 0, 0. And E2 means 0, 1, 0, 0. Then we have 0, 0, and then 1 and 0. We have 0, 0, 0, and 1. So this is E1, this is E2, this is E3, this is E4. So once we have the spanning set of R4, which is certainly the E1, E2, E3 will span whole R4, then this FE1, FE2, FE3, and FE4 will span image of R, image of F. So if this information we have, what is FE1, we can calculate because F is given already 1, 2, 3, and FE2, FE4, and so on. So we have this, this, and this, and this, these four vectors which span F4, and these may not be bases because this is just a spanning set. We got the information of spanning set, and we need to find the linearly independent spanning set basically, because these vectors may be linearly dependent. So just to find the linearly independent vectors among all these four, what you do, you write down this as a column, here also as a column. I have explained this process in the lecture very well, and this also put in the fourth column, and then do the row echelon form, and then you realize that this is a pivot element, this is a pivot element. So if we pick this and this element, that means the first and the third, the first and this third element, that will be linearly independent. All other are depends on this one. So this and this forms a basis of image f. So the dimension of the image f is 2. So hence the dimension of the image f is 2. The last one is the kernel of f. That means we have to find all x, y, z, t, which gives, we put the image to the 0 vector in R3, and then we have from here, because the image, the f is given, we can have these three equations, because this will set to 0, this will also set to 0, this will also set to 0. We have a system of linear equations, and then this is the A, and we can reduce it to the echelon form to realize that whether the solution exists or solution, what are the solution here. So the rank nullity theorem also, so the dimension of the kernel of f is equal to nullity of f is equal to 2, because we have here only 2 pivot elements. So we can generate now the solution. So Z1 can be minus 2 times any arbitrary parameter, and X can be again from here one can compute, because these are the X2, basically this can be as a mu1, and then you can take mu2. So here this, or rather we have taken this mu1 and then mu2. So from this equation we will get that this X3 or rather x, y, z. So z can be taken as this, and then x can be written from here as mu1 plus mu2. So we have the solution of this. We have the solution of this system, which gives us the kernel or the nullity of f, which is 2, and the basis of the kernel can be taken as these two, 1, 0, minus 2, and 1, 1, 0. So this was a quick overview of what we have, which is very important to understand in the vector space and indeed this linear transformation. And if you have any other question, you can get back to us. Otherwise, since there was no question in the Excel sheet or no question in the live chat, so in this case, I can end this live session with thank to all the participants. So thank you very much and have a nice evening.